Thank you all so much for coming to this session. I'm excited to talk to you today and either introduce you to or give you an update on Control Labs. At Control Labs, we're probably best characterized by our mission, which is to develop a world where computers, technology, devices, everything you've been hearing about here at ReMars, become natural extensions of your own thought and movement. We'd like all this technology that you're hearing about not just to exist, but to feel as much a part of you as your very own hand. And the way we achieve that is by connecting this technology to your nervous system as closely as your hand is currently connected to your nervous system. That's our vision. We came to this vision by looking at how we currently interact with technology today. And in particular, comparing the input that technology can give to us humans, to our nervous system, with the output that we are able to provide to the technology that we interact with. And there's a very striking gap between that input and that output. So on the one hand, even if we just limit ourselves to considering our visual processing, just a computer monitor can give us tens of millions of bits per second of input. Whereas if we think about the fastest typist in the world and calculate very generously, ignoring any language compression model, we're talking about less than a mere 100 bits per second in return. And so this is a striking problem when we think about traditional PC interfaces. And I would argue that the problem is becoming even more urgent today as computing leaves the desktop and becomes more ubiquitous. So we've gone from our PC keyboard to our mobile phones, and then ultimately to smartwatches. And at each stage, we can still get a lot of information from the device, but our ability to send information to the device is becoming more and more impoverished, to the extent that these devices are really becoming much more passive information consumption devices rather than true interactive devices. So I want to go in and look at one side of that equation, again, the human output to the device, and look at that in more detail. I'm hearing some audio, but to understand the problem here. So if we look at any of our interactions with computers, they all start with neural activity. The command is coming from you. And that activity ultimately results in the activation of muscles. Muscle activation is the only output of your nervous system. Those muscles produce movements and forces, and we as technologists and our predecessors have devised a myriad of devices, all of which really just go and measure the consequences of your muscle activations, and finally send those signals to a computer. So you see there are a number of stages here of processing, and the problem is that at each of these stages, a few things can happen. One is that you can just outright lose information. Two, you can have noise added to the information that you retain. And three, you can add latency. So considering all of that, it would be really desirable if we could just go and produce a much more direct connection from your neural activity to computers. If we could do that, we could really hope to close that gap between human input coming to the human, and output, which currently right now is so much more impoverished. So why hasn't this problem been solved so far? I think a big problem is actually with our imagination. So when many of us start to think of neural interfaces, especially the less neuroscientifically informed, or maybe the more creative of us, immediately start thinking about these wild sci-fi ideas, technology that doesn't exist yet for picking up signals in the brain. So that's one problem with imagination. The other problem with our imagination is that the more neuroscientifically grounded of us tend to have our minds very much focused on the clinical realm. And there we set the bar too low. We're fully focused on restoring lost functionality rather than augmenting the functionality that we already have. And what this talk is about is once we think about the problem in a different way and correct these flaws of our imagination, what we realize is that neural interfaces are arriving sooner than you think. They're here now, and they look like this. Nothing terribly sci-fi, just a simple device worn on your wrist. So that sounds amazing, but we'll go through and we'll see that it's actually not that far-fetched at all. And so here's the outline of the talk. I'll begin by talking about brain-machine interfaces, the traditional way about thinking about neural interfaces, where we think about signals strictly from your brain and how we can access those both invasively and non-invasively. And then I'll switch to our approach, which is about using electromyography to acquire neural signals in a different way that end runs many of the challenges that we encounter when dealing with brain-machine interfaces. And once I walk you through that technology, we'll wrap up by discussing some of the applications, both long and near term. So let's start talking about brain-machine interfaces. This is probably a relatively new topic for many of you who are much more focused on building consumer technology, say at Amazon scale. So I'll begin with just a brief introduction to signaling in the nervous system. There's really two key concepts I want you to understand, the neuron and the action potential. So neurons are the cells that perform computation in the brain. They compute the information and they send the signals. And they send these signals by way of what are called action potentials. These are electrical signals that travel along the extent of one neuron. So in this diagram here, you see a presynaptic cell on the left. It fires this action potential, this electrical pulse, that travels down the extent of the neuron to what's called a synapse, the connection between two neurons. As a result, a chemical signal is sent between these neurons, which results in an electrical input to the postsynaptic or receiving cell. In response to that electrical input, in conjunction with the other inputs that cell is receiving, it may in turn fire its own action potentials or not. A really important point to understand is that the action potentials, the signals of the nervous system, are not graded analog signals. They're quasi-digital, like the bits we use in computing. They're either they happen or they don't happen. There's no medium, small, large action potentials. For a given neuron, every action potential is the same. So here you see the voltage recording from an action potential, and what you see, so from repeated action potentials from a single neuron, and what you see is each time it fires, it has the same amplitude, it has the same duration, it has the same shape. It's a quasi-digital signal. It either happens or it doesn't. Neurons communicate not by modulating the properties of their action potentials, but by determining whether or not they happen, the precise timing at which they happen, and the rate at which they happen. So, if the fundamental signals of the nervous system are these electrical pulses, these action potentials, then if we want to record the signals from the brain, conceptually the simplest thing to do is to take an array of electrodes and smush it into the brain. And that's quite literally how an invasive neural interface works. I'm sure neurosurgeons have a much more elegant name for the process, but basically you're just smushing this electrode array into the brain. And once you do so, you have very rich signals. You have potentially hundreds of electrodes, and each of those electrodes can record action potentials from multiple neurons. And so on the right, you see some example traces. You're seeing many repeated firings of each of those neurons overlaid, and you can see each time they fire again, it's that same waveform, that same action potential that's that neuron's signature. Once you do that, you can do truly remarkable things. So here you'll see a video from the BrainGate Project, and you'll see a participant in this study who, despite paralysis, is able to use a computer operating system. She's able to, enter a search query. She's able, to then browse throughout the search results, select the one of interest. Ultimately, you'll see that she'll be able to type an email to one of the researchers on the project. So this is all extremely impressive, remarkable technology with great implications for people, say, with paralysis, but ultimately it requires neurosurgery, and so it is not and never will be for everyone. It's not the technology that we should be building for all 8 billion people of the world. So if you do want to build technology for a mass consumer market, then you have to be non-invasive. And so what are the options for non-invasively recording brain signals? The two maybe most consumer-ready of them are EEG on the left and what's NearInfrared Spectroscopy on the right. I'll talk about each of these in turn. So first, EEG. Conceptually, it's relatively similar to the invasive electrical recordings that I just talked about. You're measuring electrical potentials that are ultimately due to action potential firings of neurons. But the fundamental difference is, rather than being right inside the neural tissue, you're far, far away, centimeters away. That may not sound like far, far away, but if you consider that the diameter of a neuron is on the order of 10 microns, being on the order of a centimeter away is very far away. And so as a result, the signals you get, first of all, are greatly attenuated. They're extremely weak signals. And second of all, you're not hearing individual signals from individual neurons. What you're seeing instead is superposition. So it's a superposition of a very large number of individually extremely weak signals. And so as a result, you don't pick up on action potentials. Instead, what you can measure is the coordinated activity, large waves of activity throughout the cortex. I think the best analogy for this is probably actually the baseball stadium. You can imagine now not being inside the stadium, but actually standing outside in the parking lot and thinking about what you'd be able to hear. So certainly, if someone did, say, hit a home run, you would probably be able to hear the large roar of the crowd. But you wouldn't know, was it a home run, or was it an amazing diving catch in, say, left field? You certainly wouldn't know which team did it or which player. And the last thing you could imagine being able to hear would be the conversation between two individuals in any pair of seats in the stadium. And that's the analog of action potentials, those information-rich signals that you're going to rely on if you want to build a neural interface. There's a bigger problem too, which is that the muscles themselves generate much larger electrical fields, and they're much closer to the electrodes that you're recording from. And so say if you start doing something so terrible as chewing, you're going to completely wipe out the signal that you're trying to record from. That's not great, and I'd argue the alternative is even worse. And that's near-infrared spectroscopy. The problem here is that you're actually not measuring neural signals themselves. Instead, you're measuring hemodynamics. So that's changes in blood flow and blood oxygenation. So as a result, you have all the spatial resolution problems that you have with EEG. As well, you have temporal issues due to the time scale of the response, which is on the order of seconds rather than the millisecond time scale of action potentials. So what do we know about this response? Well, we know, for example, there is some correlation between neural activity and blood flow. So for example, if you provide a visual stimulus to someone and you image their visual cortex in their brain, what you'll see is on the scale of many seconds, there is a response. But you'll notice some problems immediately. First of all, there's quite a bit of latency. The latency is on the order of seconds. And then there's a huge amount of spread in the signal that's ultimately going to greatly limit the bandwidth that we're dealing with. But I would consider even these second-order problems. The real problem, again, is it's not the neural signal directly. And we have a relatively poor understanding of the correlation between the neural signal and this blood flow, or what we call bold response. And what we do know is about the correlation is that it itself is quite poor. And there's a number of factors that can affect it. And in addition, sometimes it's not even reflecting real activity that has happened, but it's actually anticipating neural activity that might happen or might not. And so with that, I'd just like to summarize this section on brain-machine interfaces and remind you that, again, action potentials are the key signals of the nervous system. They're the quasi-digital electrical pulses that neurons use to communicate with each other and that we should use when we're building neural interfaces. Whereas the bold signal, that's blood oxygenation and flow, is a very loose correlate of neural activity. We'd like to avoid using that if we want any great control interface. Invasive recordings allow you to get high-resolution, action potential resolution recordings, but the requirement for surgery limits them to clinical use, whereas the non-invasive approaches, unfortunately, will never allow for this signal-to-noise ratio that we will need if we want to build a high-bandwidth neural interface that ultimately, again, closes that gap between human output to technology and input from technology. So that's a rather bleak picture from someone telling you that neural interfaces are here sooner than you think. But there is some good news, and that's that if we think about neural interfaces, we can free ourselves from thinking just about brain-machine interfaces, and we can realize that the spinal cord is a way that you can, and I would argue really should be interfacing with the nervous system. And there's two reasons for that. One I'll talk about in more depth, which is technological. These are actually neurons that we can non-invasively record from with action potential resolution. And the other reason is maybe more fundamental or biological, a human factors reason. And that's that the neural activity in your spinal cord is the way that you've evolved to control the world. The only output from your nervous system goes through the spinal cord. The only output of your nervous system is muscle activation. And every muscle that you have receives its input from the spinal cord. We've never had a reason to evolve a direct connection from the brain to muscles. Instead, everything goes through the spinal cord. That is our evolved input-output port. And as technologists, we should take some guidance from evolution and what it teaches us, and we should be interfacing there. If we were making an analogy with a standard computer, if you have some new input device, you don't say, hey, let's get really close to the computation. Let's solder onto some transistors in the CPU. No, you say, let's use the proper input-output port. Let's plug into the USB. And so that we want to do the analog. And so with that, I want to talk about EMG electromyography, how we record neural signals, and how they allow for both myocontrol, control at the level of muscles, and neurocontrol, control at the level of neurons. I'll start with just a bit of background on neuromuscular signaling. And in particular, I'd like to explain the motor unit. The motor unit is the fundamental minimal unit of output from the nervous system. And when I talk about the motor unit, what I'm really talking about is the connectivity patterns between neurons in your spinal cord and muscle fibers that make up your muscle. In most of your nervous system, connectivity is quite broad. One neuron will connect to, say, tens of thousands of other neurons and receive input from a similar number, sometimes even hundreds of thousands of other neurons. Whereas the connections between your spinal cord and your muscles are much more restricted. A neuron in your spinal cord will provide output to a number of muscle fibers, but all of those are restricted to being within the same muscle. And the other direction is even more restricted. Each muscle fiber in your muscle receives input from just a single neuron. So what does this mean? This means that each motor neuron in your spinal cord has its own dedicated set of muscle fibers that respond to it and it alone. Now, these muscle fibers, from a biological perspective, are transducers. They take the electrical signal from a neuron and convert that into a mechanical signal that allows us to impart forces on our external environment. However, they also fire their own action potentials whenever that neuron fires an action potential. And so, from a technologist's perspective, we can use them as these wonderful built-in electrical amplifiers that allow us to gain access to the firing events, the action potentials of these neurons without any invasive technology, purely at the surface of the skin. Now, the other thing I wanted to talk about was motor recruitment. And so, have you ever wondered, how is it that your nervous system signals the strength with which you want to contract a given muscle? There are actually two processes that go on as one increases and then decreases the strength of contraction, as shown in this diagram. So on the left, you'll see a bunch of rows. Each row is a different motor unit, and the ticks, which sometimes bleed together, are the firing events. And what you see is as the force ramps up, more and more neurons are recruited. So they activate at different force thresholds and then deactivate when the force decreases in the opposite order. And then as well, those that are active increase their firing rates with the force level. So all this is to say that we have a really good understanding of the signaling properties of these neurons and how they relate to movement and force, a much better understanding than we have with, say, the signals in your brain. And so this allows us then to take these electrical signals that we record and very directly relate them to your muscle activations and then ultimately to your movements and the forces you generate. I think a lot of us here work a lot on machine learning, and I think we'd probably all agree that certainly currently, there is no general AI or general machine learning, and domain-specific knowledge matters. We've seen that a lot in images. For example, this is an illustration of a convolutional network architecture, and that's something that specifically looked at how does the brain, how do neurons in visual cortex respond to visual information. And then that inspired the convolutional network, which then really revolutionized image processing by computers. And what we're really doing is the analog to that, but in a different domain. Again, similar things happened in speech that allow for technologies like Alexa to work as well as they do. We're doing the analog, but for the neural signals of your body. And when we do that, we can accomplish feats like this. So here you see, well, you see what you see. We're recording the electrical signals, and then we're able to reproduce the movements of the hand, individual finger movements, wrist movements, fists, pointing, et cetera, little thumb taps, et cetera. And again, there's none of the requirements of cameras. We can do this, when your hand is at your side or behind your back. None of that matters at all. So these signals are on you. They're always with you. They're always accessible. And the cool thing is, we can pick up your intention, even if, say, some adversary is blocking what you want to do. You can still open your hand virtually, no matter how tightly someone holds it closed. In addition to your movements, we also capture your forces, so you can grasp with different strength. Here, Jesslyn is raising the bar precisely to the point where she's pointing. She has a lot of control. We can measure a number of different forces. For example, all the different finger pinches that you can perform. We can know not just which finger you're pinching, but how hard you're pinching. So ultimately, we intercept the signals that go and control your hand, and therefore have all the information about what your hand would be doing. This lets us then ultimately bypass your hand and any devices that they may be manipulating, and so we can reproduce digitally all of your natural interactions. That on its own is quite powerful and exciting, but I'd say it gets even more exciting when we start to think about neurocontrol. That's when we go from the level of muscles to controlling at the level of individual neurons. And the reason that's exciting is because per muscle, you actually have hundreds or thousands of neurons coming in. So if we can achieve this, then there's a potential massive increase in the dimensionality and the bandwidth of signaling that we can then use in our control systems. And so the first question is this possible? Can we as humans control individual neurons? And the exciting thing is that the answer is yes, and it's actually something that we've known about since the 60s. The experiments were done a little bit differently back in those days. So you would stick a recording electrode right into the muscle, and although we can do real-time spike sorting, et cetera, here you would just leave that up to the human and play the raw signal on an oscilloscope and a speaker. And once you did that, the human could use that feedback and from the same muscle actually learn to activate selectively. Some studies showed up to 6 neurons. Where you would activate one. So all of these neurons on this plot are all of these motor units are from the same muscle, and someone's able to activate one without all the others, and then switch to another one and switch to another one. So they're not limited by the standard motor recruitment patterns that govern our normal behavior once you give them the feedback to learn how to do this. So that was it in the 60s, and now I'll talk about it a bit in our own hands in the present day. So we've developed this control kit device, and here what I'm showing you is actually one of the first recordings that we performed that convinced us that we actually, from the surface of the skin, have action potential resolution in our recordings. So normally we use 16 channels, but just for pedagogical purposes, I'll just focus on a single channel here. So on the bottom, you see the raw electrical recording, and we've indicated with these red dots the peaks and troughs of the individual pulses that we see. Whenever we see a peak in our signal, a little red dot. And now what you see is that the red dots are at 3 different heights above the baseline. And I just told you that an action potential for a given neuron or a given motor unit is always the same. So these 3 heights mean that we have more than one neuron being recorded on this single channel. And so now if we go to the upper right, we can look at this in a little bit more detail. Here it's the exact same data. All we've done is zoomed in a bit and then plotted a window around each of these peaks aligned to the peak. And what we see is that these events cluster into these 3 very nice clusters, each of which corresponds to a given motor unit. And so now you can imagine yourself just watching this signal in real time, and you can say, okay, whenever I see a peak, all I have to do then is look and see, okay, which of these traces in the upper right does the signal match? Which template do I match? And once you do that, you've identified which of these 3 neurons in your spinal cord has fired at that time, all non-invasively. And so here's what you can do with it. Here's Stephen, and he's showing you, first of all, playing this game normally by hitting a spacebar to jump the dinosaur. But then he actually doesn't need to hit a spacebar. He can activate just a single motor unit. And you know, he can do that in any posture. He doesn't have to move to do that. He can do that with his hand in his pocket. There's a number of great things to note about this. First of all, the timing is really precise because the dinosaur jumps precisely in response to the activation of that motor unit. There's no noise introduced by, say, the movement of your hand or the response of the keyboard button. Furthermore, it's extremely low effort. You're activating just a single motor unit, whereas a muscle has hundreds to thousands of motor units depending on the muscle. So this is just a small fraction of a % of a muscle activation. And then finally, again, because it's just a small fraction of a % of the muscle, you can then start to use the remainder of that muscle for other things and then achieve a great increase in dimensionality and bandwidth. So just to wrap up this section, again, the spinal cord is the nervous system's evolved output port. Whenever we can't in some pathological cases, but whenever we can, that's where we should be interfacing with the nervous system. EMG allows us to do that with action potential resolution. That's the finest resolution with which signals occur in the nervous system. Once we do that, we can control at the level of muscles. That's myocontrol. Or we can control at the level of neurons, and that's neurocontrol, which really unlocks great potential for high bandwidth, low latency, highly reliable interfaces, and that's the ultimate neural interface of the future that we're building. So that's the technology and the fundamentals of how it works. So now we should think about the implications. And I would stress, ultimately, this becomes the universal output, the universal control output from humans to technology. Because, again, all the other interfaces that you're working with ultimately depend on muscle activations. We're intercepting the signals before they get to muscles. So in the myocontrol realm, we can reproduce existing interfaces, but then we also have the opportunity in the neurocontrol realm to extend those interfaces. And I really say ultimate in terms of it being the final interface. We're picking up signals from your nervous system at its natural evolved output port with full action potential resolution. There really isn't anything more that you should want for control than that. So that's the future and really where the future ends. And now what I'd like to do is just talk about the present and where we are with some of the initial technology, initial applications of this technology. And I'll focus on a few key areas. One of the areas that we've looked into is XR input. We have a lot of efforts around clinical research. There's a lot of potential applications for this technology in that space. And then robotics, I imagine, is something that you want to hear me talk about here at ReMars. I understand it's a big focus, and rightly so. And then I'll wrap up by talking about productivity and what this technology can unlock in that realm. So as soon as we saw, the reconstruction of the hand and the forces that I showed you earlier, it jumped out at us, we really ought to be thinking then about what this could do in virtual reality, because there are many people working on how do you get back the hand in a way that's natural and immersive and really feels like your own hand. That's a very important and challenging problem, but I'm not going to talk about it because I think you can imagine it yourselves based on that previous demo video that I showed you. So instead, what I'll talk about is, that I think much of virtual reality and augmented reality control should be non-biomimetic. You shouldn't be controlling with your hand the way you do in the natural world, but instead you should be able to do magical things, things that you couldn't imagine doing, like spinning this object around all its different axes, quickly, slowly, pushing it away to the far distance, well out of your reach, firing projectiles, and then with the snap of your fingers, cleaning everything up and putting back to where it was before. I think once we move away from our actual hand movements, we really start to think about, okay, how can we have rich, high-dimensional control of these virtual environments and do things we've never dreamed of doing before. Another area where rich high-dimensional control is important is robotics, and there we're controlling these multi-articulated devices that don't map onto our own body plan. I'll talk about these in conjunction with some of our clinical research work, just because there's a bit of a blend there, especially through prosthetics, which is at the interface of those two realms. So there are a lot of clinical applications, which I won't have full time to talk about, but just to give a brief survey of some of them. So this technology is being used by John Krakauer to develop stroke rehabilitation technologies, and in particular, because we can pick up the finest grained output, we can pick up signals from someone who's recovering from a stroke, even when those signals are too weak to drive actual movement, and therefore they can start practicing their dexterity even before they've fully recovered their strength. And then a somewhat similar technology is being developed by Jens Bo Nielsen, but rather than having stroke, people recovering from stroke, playing games as a way of recovering their motor skill. Jens is working with children with cerebral palsy and giving them a musical instrument for really two reasons. First of all, just because music is great and everyone should be able to produce it if possible. And second of all, through controlling such an instrument, these people can then refine their motor control and improve their motor function for other activities. And finally, there's also work done also by John Krakauer to develop this as a technology used in conjunction with hand transplants. And one challenge with hand transplants is people actually have trouble regaining control of their new hand. And one thing we can do is actually let people start practicing control of a hand even before they have a hand. And this video, I think, really makes that point. So here you see that same hand model that you saw before, an older version of it. But and again, someone's moving the wrist and the fingers, and then what you'll see is actually this person's hand does not map onto the hand on the screen. However, he still has the same muscles, and so he can still generate the same signals and then ultimately learn to control that hand with fine dexterity. You'll see he'll start doing some grasps of different strengths, and then trying to point his index finger. I think that's quite remarkable and inspires us to think about applications also in the prosthetic realm. So we're working with a number of roboticists and people working on prosthetics. We started some of this work internally, actually in the run-up to Mars conference a couple years ago. Here's just sort of a fun little playing around with it, where if we think that humans and robots should be more intimately connected, well, then they better get along. Anyway, more seriously, this is a collaborator at the Advanced Physics Laboratory affiliated with Johns Hopkins, and this is the first day we gave them an early version of our technology, and you can see immediately they've succeeded in using it to drive a prosthetic hand. And so finally, I'd like to wrap up by talking about the implications of this technology for how we go about our work and how we become more productive. Just as an intro to that, in many working environments, security and authentication and privacy are all very important. And so I thought I'd show you this video. I'll show it first and then we can start. So here, what you can see is the system is recognizing that this is Alex, one of our star scientists, and he's wearing the band. And then when I put on the band, it quickly recognizes, oh, that's Patrick. It's not Alex. How does this work? So what I told you about each neuron, so each muscle fiber receiving input from a single neuron, that's actually not true at birth. And instead, that connectivity pattern happens during the first year or so of your development, and it plays out differently in each of us. And as a result, you have your own neural signature, your own neural fingerprint. My co-founder, Thomas Reardon, likes to describe this fingerprint and this technology as really being more personal than your DNA, in that even if you had a twin sibling with the same genetics, both of you would have different neural signatures. And so that allows us to create a incredibly precise authentication technology that you just get for free whenever you're using the device. It works no matter what you're doing. You don't have to perform any specific movement, gesture, signal. It's just there. It recognizes you. Once you're authenticated, then you can go on to do some other things. So you can imagine, again, going to Instagram without any login. Here you see Adam goes and likes that image and then starts to scroll around for other things in the feed that he might like. And note he's doing this without touching anything more than a blank table. So he could really do this anywhere. And this is an interface that goes with him. Once he's done with Instagram, he can switch over seamlessly to a messenger application. He can go to the text box and produce text. I mean, why not? Again, when you type on a keyboard, those are ultimately neural signals, and we can intercept those, so we can reproduce the keyboard. So Adam said hello to his friend Tane, but ultimately I'd like to say hello a little bit more bombastically, and so I'll read along for anyone who's having trouble following the screen. Hello, world. We are Control Labs. This is the future. Universal control, you'll see he can correct a typo he makes, for 8 billion people. Thanks for the applause. Maybe what I'll do now is, it seems, since we're impressed, let's just take a pause, maybe a minute or so, and just let our own imagination run on what we might like to do with this technology, what we as developers, technologists would like to build, and how we'd like it to impact our lives. Okay, well, hopefully that's enough to at least get started. There's a long future to refine that thinking going forward. So I don't want to put a cap on your imagination and follow it up with anything else. So I'll just reiterate the points that I've already made in this presentation. Again, neural interfaces are here sooner than you think. They're here now. We're shipping CTRL-kit so that we can unlock unimagined freedom for developers and technologists, or maybe freedom that you've started to imagine now. Our early focus areas are clinical research, robotics, virtual and augmented reality, and productivity. But it doesn't stop there. Ultimately, we're building the universal neural controller for 8 billion people. Thank you very much for coming and listening.